So we finished up the Unit 1 waves here on the 22nd. And as we begin Unit 2 next week, next Tuesday, we're going to be beginning on charge. But before we start that, we're going to be starting Unit X. Unit X, that's going to be the rocket or the essay. And so I've tried to put on here the days when you're going to be working on the rockets. That's going to be these purple. So we're going to be working on these rockets on these Mondays. And so on these Mondays, what I'm going to have for you is I'm going to have a video for you on how to get the first fin on. And then the following Monday is going to be getting all the fins on. And then the following Monday is getting the engine block and the nose cone on. And then the following week is getting a shock cord and you're checking the rocket to make sure it's able to launch. So that way, this first week of March, we're going to be launching in person on the 2nd, 3rd, 4th, and 5th. I'm going to be holding some distance only launches. That's going to be on the 4th and 5th and on that Saturday of the 6th. So we're going to be holding rocket launches on those days. So for those of you who are going to be coming in person, you're going to be able to launch your rocket. If you're a Tuesday, a Wednesday, a Thursday, a Friday, you're going to be able to launch on those days. For those of us who are distance only, you're going to be able to come on the 4th and 5th after school, or on that Saturday. And we're going to be able to have a sign up form when you're saying you're going to come, and we're going to get to all that. But on Monday, we're going to be expected to start building our first rocket fin. So I have some videos. You're going to see these videos. They're going to be posted here in this Unit X, rocket or essay. All I have in there right now is the essay. And so I have in here the essay that we're going to be able to do for those of you who choose not to build this rocket. So over the course of the quarter, we are going to be working on building our rocket. If you choose not to build or launch your rocket, you will be working on your essay. We are building our rocket over time, and you should be working on your essay over that time as well. It takes time and dedication to build the rocket successfully and to launch that successfully rocket. Therefore, if you choose to do the essay, you must put in the same time and dedication over the entire quarter. And there is no this essay is in no way doable the night before it's due. So I put up here, if you choose to do the rocket, you can build it, launch it, and then have fun doing so with a hands-on, enjoyable, and memorable experience. If you don't want to build and launch the rocket, you are to choose 18 of the 21 given prompts, and you have to address each prompt in the form of a CER. And if you plagiarize, like if you just go to Google and you look for the first Google response and you copy and paste, well, that's plagiarism, and plagiarism in any form will result in a 0. And I want to make this clear here as well. There's no half credit, no partial credit, no points for trying. So you got to get it, and you got to get it all. I'm not taking half. I'm not taking partial. I'm not saying I'm not going to take, I tried. No, you got to do it. And so you are given the entire quarter to do this. And so therefore, with that, lateness will be taken into account. So a lot of the stuff I'm doing right now, if you turn in late, I don't take any late points off. But if you're going to be turning this in late, I'm going to be taking late points off. So our essay is going to be due at 8 a.m. on Monday, March 8th. So when I'm talking about this essay, there's going to be 18 prompts you have to address. I'm giving you 21. And I want you to address these in the form of a CER, where you're going to make a claim based on evidence and reasoning. So like I can just go to any one of these. We can look at how does a changing magnetic field charge your phone? And so that's one of the things that we're going to be getting into over the course of this semester or over the course of the quarter. But you have to tell me then, make a claim saying how a changing magnetic field will charge your phone, then provide evidence why that changing magnetic field will charge your phone, and then give to me then the reasoning of how that evidence supports your claim. So you got to try to answer this in the form of that CER. There's other stuff you can describe. I want to know the positive impact of physics on society. So you can make a claim about the positive impact of physics on society, give evidence, and then reasoning saying why that is so. So I've given here 21 possible questions to address, possible prompts. You got to choose 18 of them. Now, this is for those of you who choose not to build the rocket. If you're building the rocket, you're not doing this essay. I'll say that again. If you're doing the rocket, you are not doing the essay. So I want us to be clear on what is expected on this. So I'm going to go back to the materials, looking at our calendar for this entire quarter. starting Monday, I'll think about that. So starting Monday, the 25th, that's this next upcoming Monday, that's when we're going to be starting with our rocket. So I'm going to have 3 videos for us to check. 1, I'm just showing you the materials we got in that rocket bag. 2, I'm showing you how to sand our fins. And then 3, I'm showing you how we're going to glue the fins together so that way we get our first fin on our rocket. So I'm getting asked a question here. If you do the essay and the rocket, can you get extra credit? I'm going to say yes, but I'm not going to take to where you do 2 questions or you do 3. I want 18 of the 21 prompts addressed. So that might be something else. I do have other extra credit assignments along the way that I've tried to embed because I know some of us, we might not want to try to do waves. I'm also going to try to have other things along the quarter here as well, where if you don't want to do this, I'm going to have, hey, maybe you can build this and we can see how that works. So I'm trying to embed that as well over the course of the quarter. So starting Monday, you're getting that first fin. Do I have any questions about our rockets, the essay? Do I have any questions on that? So you get the rocket supplies from me. When you picked up your packet, you were able to pick up your rocket supplies as well. So if you have not picked up those the rocket kit, email me and then we can coordinate a way to get it together. So the way it works is we have our student support center here at Monte Vista High School. That's that brand new building that we just built here. We have a ticket booth where we will have materials there, but you got to let me know so that way I can bring a rocket down there and I don't just have boxes of rockets down in a location. So if you email me saying, hey, I want to come pick up my stuff, I'll bring it down to the ticket booth. And then you're going to be able to arrange a way to get to here, or you can say, hey, Mr. Enos, I'm going to come to Monte Vista High School on Tuesday at 1:30 in the afternoon. Can I meet with you so that way I can pick up my rocket? And then I'll say, yes, you can meet with me on Tuesday at 1:30 in the afternoon. And then you can come in and pick up your rocket. Or you can just pick it up at the ticket booth at the brand new building. But you got to let me know so that way I can put the rocket down there. Do I have any other questions about these rockets or the essay? Fantastic. So what we're going to be focusing on here today is going to be this wave equation. So recall 2 days ago, we got into this wave equation where we said V is going to equal to F times lambda, where F is that frequency and that upside down Y, that's that lambda, that's that wavelength. So we're going to use this equation here today to try to calculate some wave speeds. So what I'm going to ask us to do is let's get to unit 1 waves. So we're going to get to unit 1 waves. And what I want us to try to get to is let's get to this waves question number 6. We have the speed of sound in water. That's this 1400 meters per second. I want to know the frequency of a sound wave in water when the wave has a wavelength of 20 meters. So what I'm going to ask that we do, can we please address waves question number 6? Hey. All right, done. Because right now we're in Zoom. So I want you to go ahead and get to our Schoology page. You know how to get to Schoology? Fantastic, man. So from there, I want you to get to our, from that, it said there's like a Zoom link. I want you to go ahead and click, and I want you to join onto the Zoom, okay, man? Yeah. Every day. All right. We're doing it every day from 8 o'clock to 9 o'clock. And what I'm doing is I'm giving you the answers. Okay. Emails and videos and stuff, but it's all good. It's all good, dude. Start now. So what I'm doing is I'm just going over some stuff. So you got a packet right in front of you now. We're gonna be doing some of that going forward. All right, dude. All right. Get to that Schoology page. Now go, just click on materials. And just wait a minute. And then it will show up on that front screen. And then it'll be like a big old green link. I'll scroll down a little bit. It's gonna be down a little bit. Right there, that big old green line. All right, everyone. I'm back now. So on that warm-up question that we had, we're using this V equals F times lambda, where the V was given as a 1400 meters per second. The lambda, that's the wavelength of 20 meters, and we're asked about this frequency. So we can solve for the frequency. The frequency is that velocity divided by the wavelength. That wavelength is that upside down y, that lambda. So that's going to be this 1400 meters per second. And this is going to be on that wavelength of 20 meters. And this is where I get my handy dandy calculator. And we get a number of 70. And I get my units here, meters, cancel out with meters. So I get 71 over seconds. And what that tells me is that inverse seconds is 70 times per second. Man, that's gonna hurt you. So we get our frequency here to be about 70 hertz. So when I was looking, I saw a lot of you guys were able to get to that and able to get to this 70 hertz. So that's what you're to put into your answer. If you got something else, that's okay. I just wanted you to try here today. I wanted us to try the thing that we were doing 2 days ago. So what I'm going to ask that we do now is let's get to this packet. So let's get to this packet we got here. I got my SpaceX sticker. And let's open this up to pages 2 and 3. So on this first one, you got an A, B, C, D, E, F, G. I want us to try to label this wave as best as we can. So A, a B, a C, a D, E, an F, and a G. I want you to try to label this as best as you can. I'm going to give you guys about a minute, 30 seconds. Then we're going to come back and we're going to get this together. Ah. All right, let's bring it back, everyone. All right, let's bring it on back now. So this is what I was getting for our waves. That this letter A is this peak. Going from peak to peak is a wavelength. Letter C going from this line all the way to the top of the wave, that's that amplitude. That line is known as the equilibrium. So going from the equilibrium line to the top of the wave, the peak is the amplitude. Letter D, that's that trough. That's the bottommost part of the wave. E is also the amplitude going from the equilibrium down to the trough. And F is also a wavelength. It's one complete cycle, one complete wave going from up to down to back up. So that's one complete wave. So that's a wavelength. And then letter G, that is the equilibrium. So in other words, if I was to make this wave on a rope, I have to shake it. If I'm not shaking that rope's going to stay the same. It's going to be just like this one line. It'll be at its equilibrium. But if I'm not shaking that rope, then there's no wave going through it. And so we know that waves have to carry energy. So that's what we got here for this number 2. That waves carry energy from one place to another. And the highest point on a transverse wave is the peak, the crest, while the lowest part is the trough. The amplitude is the height of that wave. And the distance from one crest to the next is wavelength. So now that we know waves carry energy, we can look below where here now we're going to see a set of waves. And so as I look at these sets of waves, I'm going to point out what one complete wave is. It's where the part that I have highlighted, this is one complete wave. So what we're trying to see is how many waves are in this part right here. So in this part, I have one complete wave at least. I also have that this part right in here is half a wave. So this first part is half a wave. And there's another half. So what we're seeing in this letter A for number 6 is that we get one complete wave plus another half. So we have 1.5 waves. And so in order to label that, I have 1.5 wavelengths. As I look to letter B, I see I have going down to back up, then going down. So it's one complete cycle. So I have one wavelength here for this letter B. As I look to letter C, I have one complete wave. And then I have another complete wave. And then I have a half. So here I have 2.5 waves. And then this last one here, letter D, it goes up to back down, so I have half a wave here. So we can look at these, which ones has the biggest amplitude. That's going from the peak to the equilibrium, or this peak to trough, which one has the biggest separation between the two? Well, we can see that letter A has the biggest amplitude, the biggest part going from this vertical separation. We can also look then the one that has the shortest wavelength. Well, we know one complete wave going from here to here, that's lambda for this first one. B, lambda goes the whole way. Letter C, lambda goes to that, and letter D actually is going to go probably out to like that. So if we're looking at the shortest wave, I'm going to say is letter C, and the longest wave I'm going to say is letter D. And I'm saying letter D for the longest because if this wave was to make one complete wave, we only have half of it here. The other half will be coming out over there. So that would be the other half, making letter D be the longer of the 4 waves. We also looked in our notes when we talked about period frequency. We also were able to say that something about how period and frequency are related. We also have something about how wavelength and frequency are related. We also have something about this wavelength and period. So I'm first going to take us back up to the front here. So we see that this T is the period of a wave. The period, that's the time for one wave. The frequency the frequency, that's the number of waves per second So we have a relationship here between frequency and period, and this period and frequency. And we also have that this wave speed is equal to this wavelength times frequency. So we have this stuff here. We're going to be able to use this to make our relationships. So we want to express in words and mathematically the relationship between period and frequency. Well, we know period and frequency, we have that relationship where this period was equal to the inverse of the frequency. So in terms of words, I'm going to just kind of use symbols. So as frequency goes up, the period goes down. So that's my written relationship. That's my words. As frequency goes up, period goes down. I don't want to write too much more. I could say that they are inversely related, but that's 2 words I gotta write, and I don't like writing words. We also know that this wavelength it doesn't equal to, but the wavelength arises from, it's sort of like this inverse relationship to the frequency. And that's because of the wave equation. If you remember this V equals to F times lambda, where the wave speed was constant. So V is constant. So since the speed in a medium is constant, as frequency goes up for that wave, then the wavelength has to go down as well. So we see that this wavelength, it relates to the inverse of the frequency, where if the speed of the wave is constant, then as one number goes up, the other number has to go down. So then if we see that this wavelength is proportional to this inverse frequency, and the period is proportional to this inverse frequency, then the wavelength and the period of a wave, they are proportional to one another. So as the wavelength goes up, then the period of the wave also goes up. You could use more words saying that the wavelength and the period of the wave are directly proportional, but I don't want to say those words because, well, I don't want to. So we have here for our number 7, let's now take it over here to number 8, where we're now going to apply that wave equation. So now that we have our wave equation, we have the relationships down, we talked about waves, what they carry. We want to know the wavelength of some waves. So on this, we have the wave speed. There's a V. And we also have the oscillations per second. So that gives us the frequency. So we know the frequency is 10 hertz. So if we're asked for the wavelength of these waves, well, we know that V equals to F times lambda. And we want the wavelength, so I can solve for that. The wavelength is the wave speed divided by that frequency. The wave speed is 300 centimeters per second. We're going to divide by the frequency, 10 hertz. (300) divided by 10. We get 30 centimeters, which is also 0.3 meters. So we already came up with the relationship between wavelength and frequency. And we said that as frequency goes up, and wavelength is going to go down. So the wavelength will decrease. So if you increase the frequency of the wave will get shorter. The wavelength will become shorter. Continuing on from number 9. We have 2 docks. And it says that they're with these 2 docks, they're separated by 40 meters. So going from here, 40.0 meters is the separation. And what we're seeing is there's a crest at each dock. So a crest and a crest. And then we're also seeing there's 3 other crests. So 1, 2, and 3 other crests between the 2 docks. So then what I'm going to do is I'm just going to, well, connect the waves. I know they don't look perfect, but all we want to do is count the number of waves. So going from here to here, that's one wave. So this is one wave. It's two waves. Three waves. And four waves. So we have four waves in 40 meters. So our wavelength is going to be 40 meters divided by 4 waves, which will then be 10 meters. So then in letter B, we're getting 10 waves to pass the dock every 16 seconds. We want the period and the frequency. Well, the period, that's the amount of time it takes for one wave. So time for one wave. So I'm going to go 16 seconds divided by the number of waves, divided by 10 waves. That's going to give me a 1.6 seconds. That's the time it takes for one wave. To get the frequency, I can do the inverse of the inverse of 1.6, or I could just do, it's the number of waves per second. So I have 10 waves over 16 seconds. Divided by 16, we get a 0.625. Hertz. So now we can calculate the speed of the wave. It is V is going to equal to F times lambda, where our F is that 0.625, and we're going to multiply by the wavelength, so 0.625 hertz, multiplied by 10 meters, take that number, times 10, and we get a 6.25 meters per second. So we have the wave speed, we have the frequency, the wavelength, and the period. So as we move down to number 10, we see that the wavelength of a sound wave in this room has 1.13 meters and a frequency of 301 hertz. And so what we're going to try to do is calculate the speed of sound. So if we know the wavelength and the frequency, the speed of sound is just that V equal to F times lambda. And then when you get down to here, you're going to take the frequency and you're going to double the frequency. But what happens is the speed is constant. Because the medium is constant. Hold up, not yet, man. So the speed is constant because the medium is constant. So what happens, the speed doesn't change, the frequency goes and doubles, and the wavelength cuts itself in half. So that can sort of tell you. So the thing you got to finish up is letter A and letter C. When you finish up letter A and letter C, you got to show the calculation for the wave speed, and you got to say what happens to this wavelength if you cut the frequency in half. So you have a good start here. I want to say thank you for coming out. Thank you for being here today. I'm going to remind you to check on Monday for that Unit X. You got to get started on building your rocket. If you haven't started building your rocket, then you're going to be behind. And then you're going to be doing up that essay. I don't want you to do that. I think the rocket is going to be a lot more fun. So let's get to it. On that note, thank you very much and have a great day now.